Hello, welcome back to my channel. In this part, we'll continue our discussion on different methods of defining geometry inside of Simscape Multibody. Before we dive into extrusions and revolutions inside of Simscape, it's best to know that for most of the cases, importing an external CAD file is a much faster and efficient method than these complicated ones. And only if solid models need to be parameterized for shape optimization or for other similar purposes, one should employ these methods. Okay, with that sorted out, let's head on to regular extrusions. If a planar cross section is pulled in the direction perpendicular to its plane, it's called an extrusion. Extrusions with the cross section of regular polygons can be easily created by defining three parameters: the number of sides, outer radius, that is the radius of circumscribed circle, and the length of extrusion. For example, setting the number of sides to be 6 inside regular extrusion will create a hexagonal prism. Using larger number of sides, this method can also be used to generate approximate cylinders. For instance, here I'll create a prism using a regular polygon of 40 sides. For the length of 1 meter, this shape almost looks like a cylinder, doesn't it? This could be useful if a cylinder's tangent face is required to be used as a reference frame during modeling. Simscape allows not only regular polygons but any general cross-section to be extruded. For that, we will have to learn about general extrusions. Basically, what general extrusion does is that it takes a matrix with the coordinates of the vertices, joins those vertices with straight lines to form an enclosed cross-section, and then extrudes it up to the length provided. Note down that the vertices inside the matrix need to be ordered in the counterclockwise direction. Vertices arranged in the clockwise direction are not recognized. Let's take a look at the default matrix for general extrusion. If we look carefully, the vertices are in fact arranged in the counterclockwise direction. The vertices referred by the matrix is shown in this figure. Taking this idea, let's make a star-shaped plate with the following cross-section. However, this time will spare us some time by using a predefined variable named chamfer that has the matrix with all its vertices sorted in counterclockwise direction. Let's head on to the solid window. And under general extrusion, mention the name of the variable chamfer, hit F5 and then fit to view. Click on the top view to see that this is in fact our cross section. Let's see what would have happened if the vertices were sorted in the clockwise direction. Let's go to the command window and define a new variable clockwise equals flip of chamfer. Let's repeat the same procedure. This time we get an error because the vertices we specified were not in counterclockwise order. Extrapolating this information, we find out that it's possible to generate any cross-section if we have the vertices available in the counterclockwise order. So why not generate a standard NACA 2412 airfoil extrusion with the vertices data provided in the internet? Let's create a matrix NACA and copy and paste the vertices data from the internet. In the cross section, let's refer the variable NACA and update the visualization. And there is our airfoil. In the next video on this series, we'll learn how to generate more complicated general extrusion profiles using MATLAB functions. Before we end this video, let's learn about revolutions. Any enclosed cross-section when revolved around an axis of revolution will generate a revolved solid. Under revolution, the cross-section of the revolved solid is defined just like in the general extrusion. The axis of revolution is always the primary z-axis. Let's take the default example. This vector represents a rectangular profile on the right of the z-axis. Even in this case, the vertices of the cross-section need to be sorted in the counterclockwise direction. When we hit F5, we see that the revolution of a rectangular profile offset away from the z-axis gives a ring shape. We may again extrapolate this fact and realize that we can easily create mechanical shafts if we have the vertices of their revolution cross sections. Let's assume a shaft as in this figure. We'll need a matrix with 12 coordinates for all the vertices of the shaft arranged in counterclockwise order. If we have this data, then we can go to revolution and under cross section mention the variable with the vertices data. In our case, it is shaft. Now let's go to revolution and mention the variable shaft under cross section. We want to do the full extent of revolution, and now after pressing F5 we see that we have successfully created a shaft geometry using a revolution of cross sections.